Hey guys, this is part 2 of chapter 7, and we're going to cover a lot of math this time. It's going to be the mole, a lot of calculations involving the mole, and grams, molar mass, things like that. So we're going to learn a lot of different skills in this unit, and it will be on the exam next week. So just to reiterate something that was in yesterday's video, that the exam will be chapter 6 and 7, and it will be starting next Monday morning, the availability of it, and then it will be available until Friday night. So you have the entire week to get to it. And the way it's going to work is as soon as you open the file on Blackboard, you're going to have 3 hours, it's going to make a 3-hour countdown, that you have to complete the exam either on the Word doc or the PDF, and then you're going to submit it through Blackboard as well. And if you have trouble submitting it, you could always email it to me. But I strongly suggest trying to get it to work through Blackboard, and it seems like most of you got that for the homework too. So it's going to be a very similar process, but it's just going to be timed. Okay, so also I've had some students, some of you asked me if I was going to do a review session for the exam, because with all the circumstances, it's kind of difficult to catch on all the material, and that's a very good point. So I will be doing a review session tomorrow. So I'll be covering the main ideas of chapter 6 and 7, basically going through the study guide and reiterating what you definitely should know, because there is a lot of information. So stay tuned for that. I'll post that as well. So yeah. Okay, let's continue with chapter 7. So the mole. Now the mole is it's a number. That's all it is. It's a number. So a dozen is a representation of a number, right? So here's some examples of these representations of numbers. So like a dozen is 12. It doesn't necessarily mean 12 eggs. It can mean 12 books, 12 people, a dozen. But a mole is very similar to a dozen. It doesn't just mean, if it's not 12, it's not 500, it's a specific number. But this number is a really big number. So the mole is this, what we call Avogadro's number. It's a unit of an Avogadro's number of particles. So this Avogadro's number we use to represent molecules and atoms, and particles that are so small that these atomic particles. And here is Avogadro's number: 6.02 times 10 to the 23rd particles. It's items, particles. Doesn't necessarily have to be atoms or molecules. It could be anything. My cat is loud again. All right, so Avogadro's number, right? So you don't have to memorize it. I'm going to be giving it on the exam, and also, I mean, even if I didn't, you could look it up. But it's a very important constant in chemistry that we need to know. So really, you see it in some textbooks, 6.022. It could be 6.023, but the most important part is the 6.02 times 10 to the 23rd. That's the most important part. So the way we like to use this equality, and that's all it is. It's just a definition. It's another equality, just like we do when we convert units. 1 mole is equal to 6.02 times 10 to the 23rd particles, items, molecules, atoms, etc. So that's what a mole is. It's just this number of 6.02 times 10 to the 23rd. And just to give you an idea of how big this number is, right? So this metaphor is better to give in person, but since I can't do that, I'll just go through it. So if you maybe think for a second and think if there are a mole of trees on the earth, right? There's a lot of trees, there's forests and everything. Well, I mean, before Australia had fire, before the Amazon had a fire, think about how many trees are there were. Is there a mole? Is there more? Is there less? So you can think about that. And then let's say, so the answer is no. There's not even close to a mole of trees on the earth. There's a lot less than a mole. So then you can think, all right, what about something like blades of grass, right? And you could think, okay, there's grass everywhere. There's even grass at the bottom of the ocean. And you could think about that, okay, maybe there's a mole, maybe there's more, maybe there's less, right? But in actuality, there's a lot less than a mole. I don't know how many blades of grass, but there's a lot less than a mole. Then you could think of something even smaller, like grains of sand, right? So grains of sand is all the beaches, all the oceans, all the deserts. Deserts are huge. Like the Sahara Desert is bigger than the United States. And it's all sand, miles deep, right? And you could think, all right, maybe there's more than a mole of sand on the Earth, right? Not even close. So the amount of sand on Earth is 3 times 10 to the 18th grains of sand on Earth. That's how much sand there is. This much, right? In 1 mole of particles, there's 6.02 times 10 to the 23rd. Oh, it's just off by 5. The 10 is 10 to the 18th, 10 to the 23rd. Not necessarily. That off by 5 is huge. That doesn't mean multiply it by 5. That means you multiply it by 10 to the 5th. And what that means is you are off by 100,000. That means you would take all the grains of sand on Earth, multiply them by 100,000 in order to get the moles, in order to get 1 mole. That's crazy. 100,000 times the sand on Earth is enough to encase the Earth like thousands of miles high in sand. And that's how much sand is for a mole, for 1 mole of particles. So then the common question is, why are we using this big number if it's so big that we don't even need it for grains of sand? And the answer is atoms and molecules. Now, there's atoms, right? Let's take carbon. So in 1 mole of carbon, it's 12 grams. Only 12 grams, 1 mole. This number of particles, 6.02 10 to the 23rd particles of carbon can fit in your hand, and it's 12 grams. A mole of iron is 55 grams. A mole of lead is 200 grams, 207 grams. So all of these quantities of these atoms, you can hold a mole of their particles in your hand, and it's a tangible amount. So that's why we're using this number, to represent the incredibly small molecules and atoms that we're getting to learn, and to do calculations with them and to do reactions with them, we need to count them in terms of this mole number by maybe 1 mole, 2 moles, 0.5 moles. We're using these moles as a way of calculating a specific amount of the molecules and atoms that we're doing reactions with, because we can't do reactions with singular molecules or singular atoms. We have to use bigger grand scale numbers like the mole. So that's why we're using this number. Okay, so here's an example. So 1 mole of anything is Avogadro's number of particles. That's a very important definition I'll write down here. 1 mole of anything, I can't type, anything equals Avogadro's number of particles. That's very important. So questions that I can give you is like what is a mole? And some students say that it's the number of grams, the number of grams in a mole of something. No, it's Avogadro's number of moles or something like that. No, the mole number is just a number of particles that is in a mole. Avogadro's number of particles is in a mole. That's it. And it could be anything, a mole of anything. Okay, so here's more examples of different moles of different compounds. We normally use it for molecules, atoms, or any very small chemical, really any chemical compound or molecule that we talk about in this class. Because if we use it for trees, we can't quantify it because it's so big. This number only works for, I mean, yes, you could talk about anything with it. You could talk about mole of people, right? There isn't a mole of people, not even close. So, but you could use, normally use moles for atoms, molecules, and compounds. Okay, so the mole can be used as a conversion factor, right? And here's the conversion factor. And it kind of makes sense knowing our conversion factors already, that 1 mole is 6.02 times 10 to the 23rd particles of anything. And you can switch that around depending on what type of conversion you're doing. So let's see if we can do some examples. Okay, let's do this one. So you have how many CO2 molecules are in 0.5 moles of CO2? 0.5 mole of CO2. All right, so that's the question we're doing. All right, so let's take a look. All right, so now what we need is we're looking for how many particles or how many molecules of CO2 are in 0.5 moles. So what do we have? We have the conversion factor. We have the conversion factor of 1 mole of CO2 is equal to Avogadro's number of molecules of CO2. 6.02 times 10 to the 23rd. We have that conversion. So we have that conversion. We're being asked for, what about 0.5 moles right here? So if we know that 1 mole is 6.022, 6.02 times 10 to the 23rd, then 0.5 moles is going to be how many? It's going to be half of that. But conversion factor wise, we're always writing down our measured number, 0.5 moles of CO2. Then we're going to write our conversion factor. We want moles of CO2 to cancel out on the bottom. And we know that from our conversion factor, 6.02 10 to the 23rd molecules of CO2 on the top, that's our final unit. We're looking for the number of molecules over 1 mole of CO2. So we cancel those units out, and we get 3.01 times 10 to the 23rd molecules. So that is our conversion. And we're simply just converting, if 1 mole is 6.022 or 6.02, then how many is 0.5? That's what we're doing. Okay, cool. All right, so here we go, another one. So the number of atoms in 2 moles of aluminum is what, right? So we know that 1 mole of aluminum, of anything, is 6.02 times 10 to the 23rd. Now, what is 2 moles of aluminum, right? So you just multiply it by 2. So if you have 6.02 times 10 to the 23rd times 2, that's going to equal 12.04, right? About 12 times 10 to the 24, 10 to the 23rd. So that's what you could do, right? But this number, although it's correct, is not proper scientific notation. Our answer will not be given like this. So this is why, for scientific notation, you should always be aware of the proper notation. Now, what that means is, whenever you multiply numbers and you end up with a number that is like the number before the 10 times 10 to the whatever, this number should always be between 1 and 10. It should never be double digits. It should never be just a decimal. So it has to be between 1 and 10. Now, if it's not, like it's 12.04 times 10 to the 23rd, what you can do is you can move over the decimal point. So you can move it from here to here, like that. So I'm gonna leave it over here, and I'm gonna just say that this is equal to 1.2 times 10 to the 24th. So you're moving that decimal point over, 1 to the left, and you're increasing the number of the exponent from 23 to 24. And that is proper scientific notation. So that's our answer. And this is our atoms of aluminum. So I hope that makes sense. Okay, moving on. Okay, so we did that. Good, good. All right, so let's do this now. All right, so the number of moles of sulfur in 1.8 times 10 to the 24 atoms of sulfur is what? So it's kind of going the opposite way. We have the number of atoms, and we're looking for the number of moles. So what we can do, they have the work written for us, is we know our conversion factor. Again, same conversion factor. We're using Avogadro's number as a conversion factor. 1 mole of sulfur, 6.02 10 to the 23rd atoms. We're looking for how many moles is 1.8 times 10 to the 24th, right? If 1 mole is 6 times 10 to the 23rd, how many is 1.8 10 to the 24th? Some of you who are really good at math can already see the answer. So let's do the conversion, and you write down our measured number first, our 1.8 times 10 to the 24, and the atoms of sulfur are going to cancel out with the atoms of sulfur in the Avogadro's number conversion factor, and because we know that 1.8 times 10 to the 24 is what we're looking for. 1 mole of sulfur. Okay, sorry about that. I don't know why it cut out. But anyway, we're doing this example. So 1.8 times 10 to the 24th atoms is how many moles? That's what we're doing. So we write down the first measured number, and then we use our conversion factor of 1 mole is 6.02 times 10 to the 23rd, and we cancel out atoms of sulfur because since 1 mole is 6.02 10 to the 23rd of anything, then it's in this case atoms of sulfur, and we do the math and we get 3. So we're dividing 1 mole, the Avogadro's number, into our total number of atoms or molecules in order to get the moles. So we're getting 3. Okay, so now we can talk about moles of elements in a formula. So we have our chemical formulas. Sorry, we have chemical formulas such as aspirin, and we have this C9H8O4. Right, it's a pretty a lot of atoms in there, right? So another way we can look at moles is 1 mole of aspirin contains 9 moles of carbon, 8 moles of hydrogen, and 4 moles of oxygen. That's one way we can look at it. Because if you have, let's say you put pieces of paper, let's say you put 2 pieces of paper on a table, right? If you have a mole of tables, that means you have a mole of tables, right? And if you have 2 pieces of paper on each table, that means the moles of paper is actually 2 times the number of tables, because there's 2 pieces of paper per table. So there would be 2 moles of paper on 1 mole of tables. So this is a very similar concept, but you have in each compound you have multiple atoms. So in 1 mole of aspirin, you're going to have 9 moles of carbon, 8 moles of hydrogen, and 4 moles of oxygen. So that's important to know that. And that's how we get into our molar mass. So we talked about this. All right, so knowing that, we could do some more math. So let's just do this one right now. All right, so how many atoms of oxygen, of only oxygen, are in 0.15 moles of aspirin? Okay, so we know that in 1 mole of aspirin, there are 4 moles of oxygen. 4 moles of oxygen, right? And we know also that 6.022 times 10 to the 23rd atoms of oxygen are in 1 mole of oxygen. All right, so let's do this. So we have 1.15 moles of aspirin. So if we know that 1 mole of aspirin is 4 moles of oxygen, we can multiply this number by 4 moles of oxygen divided by 1 mole of aspirin, like that, to get 0.60 moles of oxygen. Okay, so my math is kind of weird here, but what we did was we canceled out moles of aspirin with moles of aspirin, right? There's a numerator denominator. We'll do a strike through like that. So these will cancel out, and you have 0.15 moles of aspirin times 4 moles of oxygen per 1 mole of aspirin. And that equals 0.6 moles of oxygen. All right, so now we want to figure out how many atoms of oxygen are in that 0.6 moles of oxygen. So we're going to do 6.02 times 10 to the 23rd times 0.6 moles, and that's going to equal some number. And let's see what that is. And that's going to equal 3.6 times 10 to the 23rd. So 3.6 times 10 to the 23rd. Okay, so that's that. You can check that You can go back and look at that, and here's the work for it. So yeah, what we did was we're taking the 0.15 moles of aspirin. You know that 4 moles of oxygen is in each mole of aspirin, so the moles of aspirin cancel out. And then we know that in 1 mole of oxygen, in 1 mole of anything, there are Avogadro's number of atoms. So we're using 2 conversion factors here to come up with our answer. So it's a 2-step conversion. Okay, moving on. So the next skill is a pretty easy skill, and it's called molar mass. So molar mass it's a very simple skill. Really, all it is just adding a bunch of numbers together that you see on the periodic table. That's it. And you don't need to memorize any periodic table numbers, any molar masses, because they're all going to be given on the periodic table, right? So it's super easy. For example, here's sodium, right? Na. So 1 mole of sodium has a mass of 22.99 grams. That's the average atomic mass of sodium, and that also means the molar mass. So 1 mole is that many grams. That's what that number means. So now you know how to figure out the molar masses of every element because you have the periodic table. And now you could also figure out the molar masses of every compound because you could just add them up. That's exactly how to do it. So here's our molar masses. For example, silver is 107.9, carbon is 12.01, sulfur is 32.07. So let's try to figure out the molar mass of Li2CO3, otherwise known as lithium carbonate. So here's what we know. We know that the molar mass of lithium is 6.941 grams per mole, carbon is 12.01 grams per mole, and oxygen is 16. So in oxygen and other elements, it does say like 15.99, but when it comes to rounding, just if it's something 0.99, you can round it up. If it's something like lithium, if you're in doubt, don't round it, because something like here, let's take a look. We don't have. I'll get a periodic table up. Periodic table. Okay, so let's take a look at here. Ugh, there's no molar masses on it. All right, whatever. This is so stupid. All right. So, something like chlorine, right? Chlorine has a molar mass of 35.45. That one you can't round. You can't round that down to 35 because you're missing an entire half a unit, right? So, if you don't know when to round, don't round. So 12.01 you can round. 107.9, it's not really too good to round. 32.07, you could round that to 32. But just be smart with it. And if you're in doubt, don't round it, because you have your calculators with you. So, okay, so let's do this example. Okay, so we're going to take these numbers. Here's what we're going to do. Here, we'll just do the work. We'll see the work. All right, so lithium carbonate. We're trying to figure out the molar mass of lithium carbonate. We have the formula. So we have every atom in lithium carbonate. We have Li2, so we have 2 atoms of lithium, C, 1 atom of carbon, O3, 3 atoms of oxygen. And that's what we're going to figure out the molar mass for and add them up. So that's exactly what we do. 2 moles of lithium, or 2 atoms of lithium, times the molar mass of lithium, 6.941, that equals 13.88. 1 atom, or 1 mole of carbon, times 12.01 grams of carbon. 3 moles of oxygen, 3 times 16, 16 grams per mole of oxygen, 48 grams of oxygen. And then we're going to add all those numbers up, and we get 73.89. Sorry about that. You have 73.89 grams as our molar mass. So that's our answer. Okay, so that's basically it. That's how you figure out the molar mass of anything. You just add up all of the molar masses of each individual element in the formula, and you get your answer. All right. So here's some 1 mole quantities of substances. So now this kind of goes back to the metaphor I was saying before, when we talked about how big a mole actually is, like how many particles we're talking about. Now, for grains of sand, it can't even fit on the Earth. But for things like sulfur, iron, NaCl, different sugars, they can fit in a beaker, that many particles. So that's how small, that's how infinitesimally small these particles are, that 1 mole of them, Avogadro's number, can fit in such a small volume. So that's just for you guys to know. All right, so let's do another example. Calculate the molar mass of C2H6O. All right, let's do this. Now, carbon, we know that the molar mass of carbon equals 12.01. Molar mass of hydrogen equals 1.008. And the unit for this is grams per mol. So grams per mole, G per mol. Molar mass of oxygen, and that's going to be 16 grams per mole. Okay, so what we're going to do is we're going to add all these up. So we have 12.01 for the carbon times 2 carbons plus 6, or plus 1.008 times 6 for the hydrogens, plus 1 times 16, or just 16, and that is going to equal, what do we get? That is going to equal, I'm too tired to do math, 46.08. Alright, so that's our answer. So if we do all that math, we get 46.08. Okay, so that's how you do the molar mass. So now you guys should be comfortable with doing the molar mass of really any compound. The only tough part is, let's say you're doing the molar mass of, something involving polyatomic ions, for example. So let's do another example. All right. So let's say we're trying to figure out the molar mass of CaNO3, 2. So we gotta make these like that. So we're trying to figure out the molar mass of this, right? So what we're gonna do is we can figure out the molar mass of calcium. So calcium is, what is it, 40? Let's see. Calcium is 40. So calcium equals 40, right? Now, this part, we have parentheses. So this is saying that for NO3, we have 2 NO3s, meaning we could take the molar mass of NO3 and multiply it by 2. That's what it means. Or we can distribute this 2 into nitrogen, make it N2, and then make this O6. Distribute it into oxygen as well. So I would say just multiply, take NO3, multiply it by 2. So NO3 is going to equal 14 plus 3 times 16. And that's going to equal, what, 48 plus 14, 58, 62. 62. So 62 times 2, because we're multiplying it by NO3. So we have NO3. Molar mass of NO3 is 62. Molar mass of calcium is 40. We have 2 NO3s, right? So 62 times 2 is 124. Plus the calcium, you have 40. That's equal 164 grams per mole. So that's going to be our answer. So that's how you would do something like that. Okay, moving on. We talked about that already. All right. So let's try to convert. Mass to moles. Is a really good important skill. Really important skill here. So if you have 737 grams of NaCl, how many moles of NaCl are in the box? If each box is 737, right? So we're going to use the molar mass as a conversion factor. So if you're going to have these problems, I'm telling you right now. And I would suggest the first thing you do is always determine the molar mass of whatever compound you're given. That's always the good first step, because if you're lost, if you don't know what to do, that molar mass might help you. And it probably will. If you see a formula, calculate the molar mass for it, because it's a skill that you know how to do now. So we're given NaCl as our formula. Whatever, who cares how many grams of it we have? We're given NaCl. So that you can figure out the molar mass of that. Now here, that's exactly what we do first. So Na is going to be sodium 22.9. There's only one of them, so 1 times 22.99 plus 1 times 35.45 for chlorine. Add them up, you get 58.44 grams per mole of NaCl. So that's our conversion factor. So we're writing the molar mass as a conversion factor here. So 1 mole of NaCl is 58.44 grams because we calculated that as our molar mass. Next, we're going to see how many times 1 mole of it, 58 grams, goes into our original sample. Our sample is going to be 737 grams. So we have 737 grams of NaCl times 1 mole of NaCl is, or per, 58.4 grams of NaCl. So the grams of NaCl cancel out. You're basically dividing 7.37 divided by 58.44, and you get 12.6 moles of NaCl. So you can rewind, take a look at that. So basically, you're taking the molar mass and you're kind of dividing it into your sample size in order to get the moles. So it's just using molar mass as a conversion factor. All right, let's do another example. Okay, so a sample of water has a mass of 59.8 grams. How many moles of water are in the sample? Okay, so water is our formula. Even though they don't give us a distinct formula, we know that water is H2O. So we're going to find out the molar mass of H2O. That's the first thing we're going to do. So hydrogen is 1. I'm going to round here. So hydrogen is 1, so 1 times 2 is 2, plus oxygen is 16, so that's going to be 18 grams per mole. Okay, so now our sample is 59.8 grams, and we want to see how many times, or how many moles of water are in that sample. So we're going to take that many grams of H2O, multiply it by 1 mole of H2O is, or per, 18 grams. So grams of H2O. All right, so what we're doing is the grams of H2O are going to cancel out just like before. Like that. And we get 59.8 divided by 18. And that's going to be equal to, here we go, just like this. And we get 3.32 moles of H2O. So very similar like we did before. Okay, so knowing this information, we can now go in every direction. So right now we can go from moles to molecules. We can go from molecules to moles. We can go from grams to moles. We can go from moles to grams. So we can do everything. Now here's how the book summarizes it. I don't like this. This is stupid. This is too complicated. So here's what I put, and this isn't in the slides. I think I'll definitely put it in the slides and upload them. But here is a summary of all the different math we did, and it's very easy. So here, I'll explain it to you. Now, what this is I would suggest if you're studying, memorize this. If you memorize this, it'd make it so much easier. And if you're able to write this down, it makes it super easy. All right, so we have grams on the left side here, right? We have moles in the middle, and we have number of atoms or molecules on the right. So we did all of this in different steps already, but let's just take it into one picture. So let's say we have the grams of something, like the salt, right? 700 grams, and we want to go to moles. So we're using a conversion factor. We're using the conversion factor we're using to go from grams to moles is the molar mass, atomic weight, or molecular weight. Same thing as molar mass. To go from grams to moles, we are dividing, so you just follow the arrow, dividing by the molar mass. So in the middle here are the conversion factors. There are 2 conversion factors you need to do any calculation in this schematic, and that's the molar mass and Avogadro's number. So from grams to moles, we are dividing by the molecular weight, dividing by the molecular mass, molar mass. To go from moles to grams, we are multiplying by the molar mass. To go from moles to molecules, right? So moles is a very small number. 1, 2, 3, right? Molecules is huge. 10 to the 23rd, 10 to the 24th, right? So to go from a small number like moles to a large number like atoms and molecules, you have to multiply. So you're multiplying by Avogadro's number. And to go the opposite way, you are dividing, going from a really big number in atoms and molecules to a really small number like moles. You're dividing. So you would take the atoms or molecules in your sample, divide it by Avogadro's number in order to get the number of moles in the sample. And then from there, you can make it to grams. If you know what compound you're talking about and you have the molecular weight, you could do the moles times the molecular weight to get the grams. So you can get all three of these numbers for a specific sample. Yeah. Okay, so the homework has examples of this, and also there's a worksheet. There's a molar mass worksheets, there's mole calculations worksheets, the ones that are not graded on Blackboard. Those I suggest doing. So during the review thing I post tomorrow, I'll go over this in a little bit more detail, but I definitely suggest for the rest of the week studying this, and if it makes it easier, memorize it, because it just makes it a lot faster. Also, just keep in mind smart calculations. Just be smart with it, because you see that grams is going to be a big number. Grams is going to be bigger than moles, right? So if you have, let's look at an example of that. Here, this water example. So your grams is 59.8, and your moles was what? 3. So grams is always bigger. So in order to get from grams to moles, big number to a small number, we're dividing. Dividing by the molar mass. In order to get from a small number to a big number, we're multiplying. See, every time you go from moles to something else, meaning this green arrow or this green arrow, you are you're multiplying, because you are getting to a bigger number. So that's important. Anytime you're going 2 moles, you're dividing. So that's good to know. Okay, moving on. So the last thing we're going to cover is mole relationships in chemical equations. And this is not too bad. It sounds more difficult than it is. So basically, the way we learned our equations yesterday in the other video. Now, what we can say is that we can read our equations differently. So normally, the way we read them yesterday in the other video was 2 atoms of iron react with 3 atoms of sulfur to create 1 molecule of this, right? But the way you can do it is in mole ratios too, just like this picture shows. So you can say that 2 moles of iron react with 3 moles of sulfur to create 1 mole of Fe2S3. So that's what you can say. You can say this is in a mole quantity. And that makes sense because of the law of conservation of mass. So, and here's showing that right now. If you react 2 moles of Ag and 1 mole of sulfur, it creates 1 mole of Ag2S. And you can see how the masses add up perfectly. But for our intensive purposes, I know I'm skipping some slides here, but it's not important. Our intensive purposes, we want to be comfortable with reading our chemical equations as our coefficients. Remember these coefficients we added when we balanced yesterday? These coefficients are going to be number of moles. So here's a perfect slide. We can read 2Fe as 2 moles of Fe, 3S as 3 moles of S. And when there's no coefficient, that means it's just 1. 1 mole of Fe2S3. So we can read it like that. Why is this important? It's important because we can figure out the mole-to-mole ratio between different reactants. So for example, if, let's say, in this same equation, I want to give you a question, how many moles of Fe will react with 6 moles of S? Not 3, but 6. Since we know 2 moles of Fe react with 3 moles of S, then 4 moles of Fe will react with 6 moles of S. So using that molar ratio, it can help you determine the reaction quantity, meaning the reaction ratios, or how much reacts with how much, basically. And then with that mole ratio, you can also turn it into grams, but that's not really too helpful. But it is if you're doing experimental work. So, so yeah, in the lab that'll help, but you guys aren't in the lab anymore, unfortunately. Okay, so let's do this one. So consider the following equation. We have this equation. A mole-mole ratio, or mole-mole factor for H2 and N2 is what? So we want to see the mole ratio of H2 to N2. Now we know that 3 moles of H2 react with 1 mole of N2, so our reaction ratio is going to be 3 to 1. Not this 3 to 1, not A. This one makes sense, and this one doesn't. This is 1 to 2. It doesn't make sense. So the answer is B, because it's 1 mole of N2 to 3 moles of H2. The other one doesn't make sense. Okay, and then for NH3 and H2, we know that 2 moles of NH3 react with 3 moles of H2. So the ratio doesn't matter if it's products to reactants, reactants to products. It's strictly determined by the coefficients. So our coefficient here is 2 NH3. Our coefficient here is 3. So it's going to be NH3 and H2. It'll be 2 NH3s, 3 H2s. And where do we see that? We see that here. So B is also the answer. Okay. So good. All right, we'll do one more, and then I think that's it. Okay. So in this equation, how many moles of Fe? Hold on, my cat is on the desk. All right, so how many moles of Fe2O3 can form 6 moles of O2 in this equation? So our relationship we can just look at our coefficients, and we can see that 4 moles of Fe react with 3 moles of O2 to create 2 moles of Fe2O3. So the question is, how many moles of Fe2O3 can form from 6 moles of O2? Here you have 3 moles of O2. So we know that 3 moles of O2 makes 2 moles of Fe2O3. So if we want to figure out 6, if we have 6 moles of O2, 2 moles of Fe2O3 corresponds to 3 moles of O2, basically multiplying our ratio by 2. So this is 3 moles here, make this 6. 2 moles here, make this 4, right? So it would be 4 moles of Fe2O3. So just simple ratios like that. And if that didn't make sense, if I was too wordy, I'm sorry. It's written right here, so you can kind of read over this, and hopefully it'll make sense. Yeah, so there's another one. I think I put this one up. Okay, so now let's take that same problem and same equation, and we'll talk more about it. So how many moles of Fe are needed for the reaction with 12 moles of O2? So in the equation we have 3 moles of O2, and we're being asked for how many moles of Fe, right? Not Fe2O3. So you can try this on your own, but you can pause it here. But I'm just going to keep going because we're almost done. So for Fe, right, or for the equation for O2, we have 3 moles of O2. Now we're being asked for what happens if you react 12 moles of O2. So to get from 3 to 12, right, 3 to 12, we're multiplying by 4. So we multiply this by 4. All right, guys, I don't know why that cut out again, but anyway, so this is the last problem we're doing. So how many moles of Fe are needed to react with 12 moles of O2? So 3 times 4 gives us our 12 moles of oxygen. So we're multiplying our entire equation by 4. So to do that, it would be 16 moles of Fe, 12 moles of O2, and 8 moles of Fe2O3. So our answer is going to be 16 moles of Fe. That's going to be our answer. Okay. So we did that. Good, and we're done. All right. So here's some videos. Definitely look at these videos. They're going to be super helpful. Also rewind and go back and see anything you missed. And I will be posting a review probably tomorrow, or even if I get ambitious later today. Okay, so that is it. And if you have any questions, let me know or post in the discussion for Chapter 7. And that's it. So, good luck.